exponentially larger state spaces. Just as music comes from sound waves, quantum amplitudes behave like waves. Electrical circuits make incorrect outcomes cancel out while correct ones reinforce each other, shifting the probabilities. What is entanglement? Some qubit pairs behave like a single object, so that measuring one instantly tells you something about the other, even if they are far apart.
Welcome to this video on quantum statistics, starting with the concept of wave interference. Think of it like music. Destructive interference, where waves cancel, eliminates incorrect computational paths. Constructive interference, where waves reinforce, amplifies the probability of the correct solution, guiding the quantum circuit to the right result. The core difference between classical and quantum computing lies in the bit versus the qubit. A classical bit is binary, existing in a definite state of 0 or 1. A quantum qubit, however, can exist in a complex blend or superposition of both states simultaneously, governed by a constraint where the squared magnitudes of the probability amplitudes sum to 1. Quantum entanglement describes how qubit pairs behave as a single entity. Measuring the state of one qubit instantly determines the state of the other, regardless of the distance between them. This phenomenon was famously called spooky action at a distance by Albert Einstein. The quantum advantage stems from superposition, which enables exponential processing. With n classical bits, you store one value. With n qubits, you hold a superposition over two n values simultaneously. For example, 5 qubits can manage 32 values at once, illustrating the massive processing capacity. A classical bit is binary and deterministic, existing in one of two distinct states, 0 or 1. In contrast, a quantum qubit uses superposition to be a complex blend of both states simultaneously, defined by the formula shown. This equation represents the superposition state of a qubit. Psi represents the overall quantum state. The states, 0 and 1, are the computational basis states, analogous to binary bits. Alpha and beta are complex numbers called probability amplitudes, determining the mix of the two states in the superposition. The normalization constraint, where the squared magnitudes of alpha and beta sum to 1, is critical. Alpha squared is the probability the qubit will be found in the 0 state. Beta squared is the probability of finding it in the 1 state. Since the qubit must collapse into one of these two measurable states, their probabilities must equal 100%. The Quantum Capabilities Roadmap shows the progression of quantum applications. We start with optimization algorithms and move through accelerated ML, image recognition, and pattern detection. The goal is to reach new AI architectures, developing novel algorithms for critical applications like drug discovery and climate modeling. Quantum computing performs calculations at speeds far beyond classical machines, which is great for AI, but poses a serious threat to security. This unprecedented power has the potential to break most current encryption methods used in existing cybersecurity systems, highlighting the need for quantum-resistant solutions. This video will cover 4 main areas. We'll start with the motivation and real-world impact. Next, we will cover the formal definitions of P versus NP. Then, we will look at the feasibility and runtime growth. Finally, we will dive into the intuition behind nitrogen monophosphide completeness and the core difficulty of these problems. Algorithmic complexity ranges from constant time, like looking up the first item in a list, to exponential time, which is trying to crack a password by guessing every combination. Quantum computing can offer huge speedups for some problems compared to classical machines, particularly those with exponential difficulty. Comparing real runtime, even for a machine performing 1 billion basic operations per second, exponential time algorithms quickly become infeasible. With an input size of just 100, an O2-N algorithm would take an estimated 40 quintillion years. This demonstrates how exponential time algorithms exceed any realistic time horizon, even with modest input sizes. Reframing the P versus NP conjecture asks, are problems that appear to need exponential time actually solvable in polynomial time? The asymmetry between easy verification and combinatorial search explosion is the practical heart of the P versus NP problem. While better hardware can help, exponential growth still ultimately wins. This Venn diagram illustrates the complexity classes. P problems are solvable in polynomial time. NP problems are verifiable in polynomial time. The intersection includes problems solvable in both P and NP. The set of problems solvable in quantum time demonstrates the potential capabilities of quantum computation. AI is changing everything, with generative AI driving the evolution toward artificial general intelligence, or AGI, supported by machine learning and large language models. This shift will profoundly impact both technical fields like math and engineering and liberal arts areas such as sociology, music, dance, and fitness. This video is on post-quantum compute, or PQC. To ensure security in the quantum era, organizations must invest in the research and implementation of post-quantum cryptography. This is the next frontier in protecting sensitive data. The author has a strong academic and professional background, holding a BS in mathematics and passing rigorous actuarial exams. With 6 years of experience in modern computing systems, the author combines deep mathematical theory with practical implementation skills. The author acknowledges the use of several AI software tools in the creation of this video, including Gemini Pro, Perplexity Enterprise Pro, ChatGPT+, and Dolphin Mistral, along with programming languages like Python 3, LaTeX, and C++. You can follow us on our website at predictiveinsightsai.com or check out our content on YouTube, Instagram, and LinkedIn. Our portfolio is also available on GitHub,